Okay, welcome everyone to the Maths and Stats Seminar. Our first speaker today is JS Lemay, who will be telling us about fundamental theorems of calculus and Zinbiel.
Thanks. Thanks for having me. So I think this talk hopefully is accessible to everyone in all domains of math because it talks about some basic linear algebra and some things from calculus that you're all familiar with, hopefully. Just a quick introducing myself. So I'm at Macquarie University. I'm part of the category theory group over there. Feel free to call me JS. I'm a category theorist, and I've studied these things called differential categories, tangent categories, monodal category, trace monodal categories, category, and other stuff. But in my studies of these things called differential categories, well, I also pick up other important notions of differential geometry and differential algebras, which is sort of what today's story is about. And so, but really the main story is about the algebraic approaches to calculus. And as hopefully you all know, and probably you're teaching to your undergrads at the moment, there are two main branches of calculus, and they are differential calculus and integral calculus. And these two are related via the fundamental theorems of calculus. And now the use of algebraic methods to study differentiation and integration have been quite successful. So famously, the algebraic generalization of the differential operator is called a derivation. And this is something you probably have come across at some point, whether you're studying ring theory or algebraic geometry or even in algebraic topology. And derivations are particularly well known. And again, they're used all over in mathematics. In particular, the differential algebras have been well studied since the 1900s. On the other hand, there's also an algebraic version of integration, which I'll just call integration, and which is also sometimes called Rota-Baxter operators. And the integral analog of a differential algebra is called a Rota-Baxter algebra, and these have boomed in the 2000s. And so today's story is how the fundamental theorems of calculus correspond to this algebraic structure called Zinbiel algebras. So here's the main result. I like to start my main result. So if there's one takeaway from today, it's this slide right here. It's something called FTC pairs, which I will call, which is a derivation and an integration which satisfy the two fundamental theorems of calculus, are essentially given by Zinbiel algebras. And as a category theorist, I can state this result in a nice category theory way to say that there's an equivalence between the category of FTC pairs and Zinbiel algebras. Now, don't worry, that's the extent of my category theory I have in this talk. All the rest is about algebras and linear maps, and that's about it. But if you want to see the full story, well, you can see my paper that came up, I guess, sometime earlier this year. Okay, so here's the framework I'm going to be working with. So I'm going to be working over a commutative ring R, and I'm going to assume that I also have an R module M. And in particular, I'm going to be very, I'm going to write my actions and my multiplications like using a bullet and a dot. And the reason for that is that at some point we are going to be using a special kind of module action, which will be, and if I just write the module action as AM, it gets a little confusing. So it's better to just write everything using scalar bullets and dots. But for those of you that may work in more generalized settings, yes, a lot of this story can be generalized to the non-commutative case, the non-unital case, the bimodule case, etc. But that's not the point of today's talk. The point of today's talk is to give you an introduction to Zinbiel algebras. Okay, so let's start with derivations. So a derivation is a linear operator D that generalizes the differential operator. So its idea is that my capital D should take a smooth function f and send it to the derivative of f. So in terms of our algebraic setting, a derivation of a commutative ring evaluated in an R module M is going to be a function from my ring to my module such that, well, the first thing I'm going to ask is that it's Z linear. So essentially saying that the sum of the derivative is equal to, sorry, the derivative of a sum is the sum of the derivatives. And it's important that I'm saying that this is Z linear and not R linear, because if a derivation is R linear, things collapse real fast. So this is just Z linear. But we can also multiply elements in a ring. So, so we can ask, how does the derivative interact with the product? Well, we have the Leibniz rule, which of course tells us that the derivative of a product is the product of one times the function times the derivative of one plus the derivative of the other one times that function. And so we can express this using in ring theory by saying that the derivative of A times B is A scalar is the derivative of B scalar multiplied by A plus the derivative of A scalar multiplied by B. So these are derivations, and so hopefully you've come across this at some point in algebra, and if not, this is it. They are essentially linear operators that satisfy the Leibniz rule. Any questions? In the special case where my module is just my ring, we call this a differential ring. And in this case, I can rewrite the Leibniz rule because I have, my multiplication is commutative. I can just rewrite the Leibniz rule as follows, in the usual way that we are probably more familiar with. So what are some examples? So for any commutative ring, I can pick up its ring of polynomials in one variable. Then Rx is a differential ring with derivation just given by the standard polynomial differentiation. So this is sort of the canonical example of a differential ring. But I can also differentiate other kinds of things, so I can differentiate smooth functions. So if I take C infinity of R to be of the smooth function, the real smooth functions, then C infinity R is a differential ring where again it's given just by standard differentiation of smooth functions. So nothing too, so essentially we can capture the two main examples of things we can differentiate, polynomials and smooth functions. Here's an example that may not be as, a bit wackier in some sense, but still very tame. If I take a graded commutative ring, so what that means is that, my commutative ring splits off into degrees, and when I multiply things of degree m and n, I get something of degree n plus n. Now take the module where I've cut off things of degree 0. I've cut off the ground bit. Well, I get a derivation from R into R greater than 1. And there's a derivation where I just take a homogeneous element. So that means it's an element inside one of these Rn's. And I just multiply it by its degree. And this gives me a derivation. So, and this is a good example because it's not a differential ring. It's an actual derivation from a ring to a module that isn't just itself. If you know a bit about derivations, then I can't talk about derivations without talking about these things called Taylor differentials. I'm not going to spend too long on them because we don't actually need them for today's story. But the point is that for every ring, there's a universal derivation, which essentially means that for all derivations, so what essentially means that there's a module omega r with a derivation to it, such that all other derivations from r to m factors through this omega r. And this is called the Taylor differentials. We don't need to know how to build it. All you need to know is that it exists. And for polynomials, we've actually already seen it. The standard polynomial differentiation is the Taylor differentials. But for C infinity, for smooth functions, omega of C infinity r is not just C infinity r. It's something more complicated. Sorry?
But it's understood.
Yes, there's a general construction of how these things are built. And the way to build omega r is not difficult. So it's understood what it is. That's fine, and I can describe it. It's just not C infinity r. If you want C infinity r, if you want smooth functions to be universal in some sense, you have to look at a special class of derivations, but that's sort of tangent to today's story. Okay, so how should the integration analog of derivation be axiomatized? Well, it should be a linear operator P that generalizes the integral operator. So the idea is that P of F now sends F to the integral from 0 to x of F. And here I'm actually thinking of integration as anti-derivation. So really the opposite process of differentiation. So I'm not thinking of this measure theory theoretically, I'm thinking about this anti-differentiation. So if a derivation goes from R to M, then my integration should be the opposite process from M to R. So my integration goes from my module to my ring. Well, again, the first thing is I'm going to ask this to be Z linear. So again, this essentially says that the integral of a sum is the sum of the integrals. But again, very importantly, I'm not asking for my integration to be R linear. This is just Z linear. If it's R linear, things collapse. So if a derivation is axiomatized by the Leibniz rule, the integration should be axiomatized by the integral analog of the Leibniz rule. So who's teaching calculus this semester? Differential calculus, so not integration calculus. But who remembers what the Leibniz analog, what the integral analog of the Leibniz rule is? Excellent, integration by parts. Yes, so it's this formula here, right? So it's f times g minus f at z minus the lower bound, and then it's just the sum of the integrals. Okay, so I can ask for that, but what's the problem with this? Excellent. This formula has derivations in it, which is not great if I want to give some, if I want to axiommatize something integration on its own. So somehow I need to give an integral only version of integration by parts. So to do this, we're going to use the fundamental theorems. And so let's set little f to be the integral of some capital F, and let's set little g to be the integral of some capital G. Now first observe that little f at 0 and little g at 0 are both equal to 0, because the integral from 0 to 0 is just 0. So on the left-hand side of the integration by parts rule, in this special case, I get that this is the multiplication of the two integrals. Everyone see that? On the other hand, the first fundamental theorem of calculus tells me that the derivative of little f is capital F and the derivative of little g is capital G. So the right-hand side of the integration by parts rule is given by this formula here. It's sort of taking the integral of f times g plus the integral of f, capital F, times the integral of g. Then putting all of this together gives me the Rota-Baxter rule. So here is the Rota-Baxter rule. So if there's one thing to take away from my, the second thing to take away from my talk today, it's this Rota-Baxter rule here. Because most people have probably never seen it before. And this is the rule that we can use to axiommatize integration because it only has integrals. So we're going to ask that an integration from my module to my ring satisfies the Rota-Baxter rule if Pm times Pn is equal to P of n scalar multiplied by P of m plus P of m scalar multiplied by Pn. So hopefully you see that this is just how this is just changing. I just took the Rota-Baxter rule up there. Wherever I saw an integral, I replace it with P.
What is like m and n?
M in this case is capital F and n is capital G. Of course, in the special case that m is equal to the commutative ring, an integration is called a Rota-Baxter ring, or rather, most people work in their algebra case, so Rota-Baxter algebra. And the Rota-Baxter rule can be written as follows. And here's a bunch of nice references. I highly recommend this book by Guo, Integration to Rota-Baxter Algebras, if you're interested in this algebraic aspects of integration. It's one of my favorite books, and it's very well written. So any questions about the Rota-Baxter rule?
So to me, it seems like an arbitrary choice of why we made integration be m to r and differentiation the other way around.
It's not necessarily an arbitrary choice because if you think about it, derivation, like the Leibniz rule is pretty fundamental and you need to be able to express that. So you need to be able to say, to sort of multiply things together in the first place. So the domain has to have some sort of multiplication. The output codomain also needs some sort of, it needs to have some action from your input to multiply with that derivative. So it at least has to be a module. But if you want, you can just work in just rings, like differential rings and Rota-Baxter rings. There's no, like if you're convinced about that, then that's okay. Okay, so let's go through some examples. So while we can always differentiate polynomials, can we always integrate polynomials? The answer is no, right? Because if I want to integrate a polynomial, if I want to integrate x, I need to be able to divide by 2, right? Because the integral of x is x squared divided by 2. So a polynomial ring has an integration if I can invert all the natural numbers inside my ring. So if all the natural numbers are invertible, well, greater than 0, then R of x as a Rota-Baxter has an integration just given by the standard formula for polynomial integration. Excuse me. Smooth functions, on the other hand, are nice because I can always integrate them. So C infinity of R always has an integration, again, given by just the standard formula for integrating smooth functions. Now, I've chosen my lower bound to be 0 just for convenience, but I can fix any other point in R as my lower bound, and it's still going to give me an integration. Going back to my graded example, remember where my derivation was multiplying by the degree of a homogeneous element? Well, I can do the opposite process. So again, if I can assume my natural numbers are invertible, then I can multiply by 1 over the degree of a homogeneous element, and that will be an integration. So I mentioned these things called Taylor differentials, which was a universal derivation. It's natural to ask, is there a quote unquote co-universal integration, which means that every integration factors through this thing? And the short answer, well, not the short answer, the answer is no. There is no universal integration for any commutative ring. If you're curious, you can go to this link and for slides of a longer version of this talk where I do give a counterexample and actually explain why things collapse if you assume that there's a co-universal thing. But even if there isn't a co-universal thing, integrations are still interesting, and hopefully by the end of this talk, I'll convince you of some interesting aspect of them. So how should, now that I have a derivation, now that I have an integration, well, I want to combine them. I want to say, how should they interact with each other? And the answer is, they should interact by analogs of the fundamental theorems of calculus. So the first fundamental theorem of calculus essentially says that if you integrate first and you derive, you get back to where you started. That is the first, that is FTC, what I will call FTC1. In category theory terms, this is saying that integration is a section of derivation, or equivalently that derivation is a retraction of integration. So a derivation and an integration of the same types satisfy the first fundamental theorem of calculus, FTC1, if the derivative of Pm is equal to m. When my module is equal to R, and I have a differential ring that's also a Rota-Baxter ring that satisfies FTC1, this is what's called a differential Rota-Baxter ring. And these are well studied by Guo and his co-authors. So FTC1, pretty straightforward. FTC2 says the following, right? It says that the derivative, if I take my derivative and then I integrate, well, I get back my function up to a constant, right? I take the difference of the upper and lower bounds. So what this says is, again, that integration is a retract of derivation up to a constant. So first I have to address this up to a constant bit. Well, it turns out that this constant, another way to describe constants is things whose derivatives are zero. And I can do this in my algebraic world by just taking a derivation, and then I'll say that a d constant for that derivation d is just an element of the kernel of d. So it's a thing in R such that dc is equal to 0. And fun facts, d constants do form a subring, because in particular, the multiplicative unit is always a d constant. So a derivation and an integration satisfy the second fundamental theorem of calculus. If for every a and r, there exists a d constant associated to it, CA, such that the integral of the derivation of a is equal to a minus that differential constant. And I'm also going to ask that this differential constant is compatible with multiplication. And so to see why I'm asking this, it's probably better to see it in this way. FDC2 is equivalent to saying that the linear map defined as a minus the integral of the derivative of a is an idempotent ring morphism. So essentially, think of this E as the evaluation. So this CA bit is, if we think of A as sort of a smooth function, then the CA bit is just A evaluated at 0. And so that's why it's compatible with multiplication a bit. Now, to the best of my knowledge in algebra before this, I don't think FDC2 has really been considered much on its own, but it is a key axiom in the field that I study called differential categories. Yeah.
What's the compatibility equation saying? What's the C in the middle?
That's a typo. Goodness, that should be a C dot. It's just a terrible typo. It should just be CA times CB. It's just apparently LaTeX decided not to behave.
And this is like, there's like some hidden existential quantifier. Like, there's like, there exists an A and there exists a B, then
Yeah. So for every A, I have a CA, which is in the kernel. And this is what I'm asking.
because you only ask for the existence of a CA, then this holds for all of the.
Yes, but the CA is forced because of it's forced to be A minus PDA.
Oh, okay.
Okay, and then an FDC pair is just a derivation and integration that satisfy FDC1 and FDC2. When m equals r, we call a derivation and integration that satisfy both FDC1 and FDC2 something called an integral differential ring. However, if you were to open up that reference, you may say, well, hold on, JS. Integral differential rings are not axiomatized using FDC2. They're instead axiomatized by something called the hybrid Rota-Baxter rule, written out as follows. But it turns out that if you assume FDC1, FDC2 is equivalent to the hybrid Rota-Baxter rule. So integral differential rings are really the ring version of FDC pairs. I mean, as far as I can tell, I introduced this notion. So I just gave the sort of module version of an integral differential ring, if you will. So my first example is if I take a commutative ring where all my natural numbers are invertible, all of my positive natural numbers are invertible, non-negative natural numbers are invertible, then oops, that should be Rx and Rx, not Kx. And this is an FDC pair, and it's in fact a integral differential ring. If I take smooth functions, this is also an FDC pair. Not too surprising. And also my graded ring example is also an FDC pair. And this is an example that is not an integral differential ring because of course the ring and the module are different things. There's lots more examples of FDC pairs that can be found in my paper, but also out there in the literature. power series, there's nothing special about polynomials. I could do this for power series. There's something called Hurwitz series, which are the co-free differential rings. There's also free Rota-Baxter rings, and these don't form an integral differential ring, but they do have a canonical module associated to it that makes it an FTC pair. And I do have examples from these things that I study called differential categories, but I'm happy to talk about that for those that are curious. And then one question that I was sort of asked, but I'm pretty sure the answer is negative, is there's also this construction of free differential rings, which are not easy to describe. And then can these somehow be made into an FTC pair as well? I investigated this a couple months ago, and I think the answer is no, not in general, but maybe there's a more clever way to do it. I like to give separating examples to things. So here's two examples where that satisfy one FTC, but not the other. Trivially, the zero maps are always integrations and derivations, and these will satisfy FTC2, but they won't satisfy FTC1. Unless if M is non-zero, then they won't satisfy FTC1. An example of a differential Rota-Baxter ring, which is not an integral differential ring, is given in this paper by Gual and Keeger. And so if you read that, and if you remember all the definitions I had a few slides ago, this is saying that there's an example that satisfies FTC1, but not FTC2. So it's good to have separating examples as things, because then you can show that the two fundamental theorems of calculus are actually distinct from each other, independent from each other. So before I move on to Zinbiel stuff, any questions?
Two, but not one.
Two, but not one. Yeah, that's the first one. So the first one is the 0, 1. Other questions before I move on to the Zinbiel part? Okay, so now let's change gears to talk about the main result, which is I want to show that these things correspond to Zinbiel algebras. So now let's talk about this Zinbiel. So who's heard about Zinbiel before? If you stare at those letters long enough, maybe you see it.
Leibniz backwards.
Excellent. Zinbiel is just Leibniz backwards. Because Zinbiel algebras are the causal dual of Leibniz algebras. And these were introduced by Lode. I'm not under the name, they were under the name dual Leibniz algebras. I don't know who came up with the name Zinbiel algebra. Or I think I do know, but I'm drawing a blank. So what is a Zinbiel algebra? So for a commutative ring K, so I've changed my ring from R to K here, and there is a reason why I'm doing that, and it'll be clear in a few slides. But for a commutative ring K, a Zinbiel algebra is a K module, Z, equipped with a K bilinear binary operation, triangle, which satisfies the Zinbiel associativity identity. It looked kind of funny, but what this is capturing is something called the shuffle product. So if you take a deck of cards and you just go to shuffle them together like this, the order of the cards in this hand haven't changed, right? I've just shuffled them together, but the original orders haven't changed. So this is in a way capturing what's called the riffle shuffle. It's capturing something called the shuffle algebra, but I'm not going to talk more about that because I'm going to give you lots of examples of Zinbiel algebras from these FTC pairs. What's very important is that this operation is non-associative, non-commutative, and non-unital. Okay, so this is the only identity it satisfies. However, from here, I can define a non-unital, associative, and commutative operation called the symmetrized product, which is defined by taking the sum of the two versions of my Zinbiel operator. So x Zinbiel y plus y Zinbiel x. And this gives a commutative associative multiplication on my Zinbiel algebra. But very importantly, it's non-unital. It was, again, things collapse. So this is what is So today's main result is I'm going to tell you that actually Zinbiel algebras essentially are just another way to present FTC pairs. So we've already seen lots of examples of Zinbiel algebras, you just didn't know they were Zinbiel algebras. So let's go from an FTC pair to a Zinbiel algebra. It turns out that I actually don't need derivation to do this. It's actually well known that there is a relationship between Zinbiel algebras and integration. Actually, it's super well studied, the integration between Zinbiel algebras and Rota-Baxter algebras. So if P is an integration, then my module is a Z Zinbiel algebra by defining M triangle N by M scalar multiplied by the integration of N. The order is important here. Notice that M on the left and on the right, M on the right and on the left. Very important. And the symmetrized product is given by just what was the inside of the Rota-Baxter rule. But of course, note that this is a Z Zinbiel algebra. It turns out that with an FTC pair, I can improve upon this by instead asking for I not only get a Zinbiel algebra over Z, but I get a Zinbiel algebra over the constants of my derivation. So for every FTC pair, M is actually a kernel of the Zinbiel algebra with the same Zinbiel operator as before. And this is why I changed my commutative ring to commutative ring K for Zinbiel algebras, because I'm not saying that this is an R Zinbiel algebra. It's not going to be an R Zinbiel algebra, but it's going to be a constant of the derivation in Zinbiel algebra. So let's apply this construction to our FTC pair examples. So if I take my polynomial ring example, then the ring of polynomials is a Zinbiel algebra. And the operation is a little weird. You take M and N, and then you divide it by 1 over N plus 1, and then you sort of do, and then you can just multiply the degrees together. And then the symmetrized product is this weird looking formula here. C infinity R is a Zinbiel algebra, where again, you just take the Zinbiel operator, just takes a smooth function and multiplies it by the integral of G, of another smooth function. And then my graded ring example is also going to be a Zinbiel algebra, where the Zinbiel operator does the same thing. So it's like the polynomial ring example, but where you do 1 over degree of B times, then multiply A and B together, and then the symmetrized product does this funny operation with the degrees. Now, I'm not claiming that these should be natural, like you should understand what these formula means in any way. The whole point is that this gives you an alternative perspective to derivations and integrations, which I will explain in another slide. But I just want to point out that we've seen examples of Zinbiel algebras before, and they're given like this. Okay, so how do I go from a Zinbiel algebra to an FTC pair? Well, we know that if I pick up a Zinbiel algebra over K, we know that the symmetrized product makes it to associative, commutative, but not unital, right? So in my FTC pair, I should be able to give you a commutative ring. So I need my unit. And the way you do this is you just take the semi-direct product of K with this module Z. The way this is that not the semi-direct product, but you're gonna build this new ring whose underlying K module is just the product of K and Z. And then the multiplication is given as follows. So a pair AX times a pair BY, well, you're going to do just the multiplication in K. But in the module bit, you do the scalar multiplication. Sorry, these should be bullets. But then you do the symmetrized product on the module parts. Now, Z becomes a K times Z module via this action here, where you sort of do the scalar multiplication on the Z bit, and then you do the Zinbiel algebra plus the Zinbiel operator. Now, very importantly, this makes, while Z is a subring of K times Z via the, well, a subunit or non-unital ring, this modular action is different than just multiplying. So AX bullet Y is not equal to AX times 0Y. So this is a different kind of modular action. Does everyone see that, hopefully? Okay, so now I'm going to turn this into an FTC pair. So I need to give you a derivation and integration. So can just consider the simplest things you can think of, right? I need a map between Z and KX and K times Z. So what are the simplest maps between these things? It's the projection onto Z and or the injection of Z into it, right? And it turns out that this is an FTC pair. Very simple. Now, when you first see this, you might go, well, that's boring. It's a boring FTC pair. The derivation's not interesting. The integration's not interesting. And to that I answer, well, that's the whole point of the story. What's interesting here is that the multiplication is complicated. The integration and derivations are easy, but the multiplication is complicated. So that's for Zinbiel algebras. For an FTC pair, multiplying polynomials, easy. But derivation and integration, well, technically a bit more complicated. And that's where the flip is happening. That's the difference, that's sort of the mirror of what's going on between Zinbiel algebras and FTC pairs. FTC pairs, multiplication easy, derivation, integration more complicated. Zinbiel algebras, multiplication complicated, but integration and derivation easy. So what was happening, so for example, what was happening with those Zinbiel algebra formulas I gave you for polynomials and smooth functions, is that those gave us really complicated multiplications, but then they would simplify the integration and the derivation operation. So. And then to further justify what I just said, these constructions are indeed inverses of each other. So to see that, if I start with a Zinbiel algebra, build the FTC pair, well, the kernel of the projection is, of course, up to isomorphism, just my starting commutative ring K. So, and then the module beta is, of course, Z, and I do get back my starting ring K. On the flip side, if I start with an FTC pair, build the Zinbiel algebra M, and then back the FTC pair, it turns out, sorry, this capital A should be an R. It turns out that R is indeed isomorphic to the kernel of D times M. And this isomorphism comes from the fact my two FTC uses the integration and derivation, and these are isomorphisms via the fundamental theorems of calculus. But of course, as a category theorist, I can do better. So just to very quickly, I have to tell you what the categories are. So the category of FTC will be the objects are FTC pairs. And then a map between FTC pairs corresponds to a ring morphism between the rings and a module morphism between the module bits, such that they also commute, such that F and G commute in these way with the derivation and the integration. So a very natural thing to do if you're building categories. Then Zinbiel algebras are essentially built the same way. Objects are going to be pairs of a commutative ring with a Zinbiel algebra to it. Maps between them are ring morphisms between the underlying rings, and then a module morphism, and then a Zinbiel algebra morphism, which is a module morphism from Z to Z prime, such that it also commutes with the Zinbiel operator. And therefore, I can say, to state my main results in terms of equivalence of categories, that FTC is equivalent to Zin. And again, if you want to see the full story, check out my paper. And this gives an alternative perspective to a result from this paper, which, I'm gonna lie, this paper is really hard to read. And they don't use category theory, they use equivalence classes of things. They're essentially building an equivalence of categories, but without saying those words. So it's a very hard read and it's very technical. But they also don't involve derivations, which this story does. that find was pretty neat. Okay, just I have like 3 more slides where I just build a new FTC pair. So one thing I'd like to show is that, as I mentioned, from any integration, we already know that we can build a Zinbiel algebra. So that means that if I have an integration, well, I can build an FTC pair from it. But where I lose the information, again, this A should be an R, sorry about that. But where I lose the integration, I start with commutative ring. So if this thing wasn't an FTC pair to start with, I have lost information, right? That's okay. So, but I can still build an FTC pair from it. If you want to go from derivations to FTC pairs, it's a bit more complicated. I'm not going to go through this construction. I'm just going to leave it on the slide. But the reason I wanted to point this out is, while this seems a bit of an ad hoc construction, this is exactly the kind of thing that we do in differential categories to build integrations. So it's just sort of I've taken what we know how to do in differential categories and sort of applied it to this case. But it's a bit of a complicated construction that I don't think is necessarily enlightening to explain at this point. But we can go from derivations to FTC pairs with this setup on the slide. And from the setup that's on the slide, well, I can apply this construction. Again, I don't want to explain this too much, but essentially, we've already seen examples of the setup from the previous slide. Both polynomial rings and smooth functions arise in this manner, and you get this kind of stuff. As I mentioned, quick word about differential categories. So I do these things called differential categories, which essentially uses category theory to provide the foundations of differential calculus. We can talk about derivations and differential algebras in a differential category. We can also talk about integration, antiderivatives, and the fundamental theorems. That's what I did for when I started getting into research. And of course, work in progress is I'm writing up the paper where I do FTC pairs in a differential category. And the reason I do this is because the notion of antiderivatives in a differential category is completely determined by the existence of FTC pairs, which I find quite interesting. So that's it. So once again, the main result for the day is that FTC pairs, which are derivations and integrations to satisfy the 2 fundamental theorems of calculus, correspond precisely to this notion of Zinbiel algebras. Yeah, so thanks. Hope you enjoyed my talk. Because I'm a Macquarie representative, I will always throw this out. We have the category theory seminar, which both James and Ifzif have talked to. Our category, I think we're a pretty friendly seminar. I know category theory scares a lot of people, but I'd like to point out that it's very category theory loose. So as long as you have the word category in your talk, we're open to anything really. So if you're interested, please come and give a talk at our seminar. And yeah, that's it. Thanks for listening. Merci.
Thanks, JS. Any questions?
Do you have any examples of these pairs that don't have a smooth function or polynomial kind of feel to them, like some weird thing which you wouldn't expect?
Yeah. So there's these things called shuffle algebras, which are like the free Zinbiel algebras. And these, in a way, they're expected because when you do this construction on the shuffle algebra, you get free Rota-Baxter algebras. So, but the integration and derivations are kind of wacky in the sense that they're kind of just shifting a tensor to the left or the right. So that's one example is shuffle algebras and free Rota-Baxter algebras. I think Hurwitz series, if you have never seen a Hurwitz series before, that would be a new example, but Hurwitz series are closely related to power series.
So another question about examples, if formal, Laurent series, rational functions? Do these give examples?
Yes, those definitely do give examples. I mean, they give not only are they rings, they're going to be differential fields. So those are examples of those kinds of things, or differential fields.
You mentioned sort of this, on the one side, multiplication's easy, integration differential, I think integrating, differentiating is hard, and then it sort of flips on the other side.
Yeah.
Do you see that there might be some value in using that duality in, say, first year calculus courses?
No, I mean, no. I think the Zinbiel algebra bit probably is too, like, it's too much for students. I do think there is value in teaching this algebraic approach to differential calculus where you don't have to, you don't do the epsilon delta thing first. But it's sort of a chicken and an egg story, right? I can build these algebraic approaches, but then I want to give examples. And to give that example, I have to do the delta, epsilon delta thing. But then from the epsilon delta thing, I get my Leibniz rule. So it's a bit of a chicken and an egg story, but I do think that this notion of FTC pair is pretty easy, that hopefully, maybe not a first year student, but maybe a second or third year student who has done a bit of modules and group theory can use, yeah. But Zinbiel algebra, I think, is probably maybe a third or a fourth year student probably would understand Zinbiel algebras, but I don't know if this.
Well, I was thinking more not in the, like, say there's a Zinbiel algebra, but obviously like it's hidden under the hood.
Yeah.
So take some key ideas.
Yeah, definitely. I mean, I think the Zinbiel algebra bit is a powerful thing when it comes to integration, because it's got this, it's telling you, it's essentially doing integration by parts is essentially the Zinbiel associativity axiom. So, yeah, maybe there's something there.
I was just trying to wrap my head around the third of the examples that we can actually say. You have the polynomials,
Yeah.
Smooth functions, and then this graded thing.
Yeah.
Can you see polynomials as graded?
Yes.
And then apply that, and then you're just saying the derivative of x to the n is n x to the n.
Yes, so that's exactly what's happening. So I got this slide here. And so that graded, that's the this is the polynomial version of the graded example. But it turns out that those two things are equivalent, they're equivalent as FTC pairs, but they're definitely different. And yeah.
So is there some kind of way to understand what? So okay, if you're doing calculus and you do the epsilon delta stuff, then the derivative is n x to the n minus 1.
Yes.
Is there a way to understand n x to the n as some kind of geometric?
Yes.
Thing to be doing?
Yes. So yes. So the way it works, what's happening under the hood is really you're doing f of x, and then you're sending to f prime x dx, and that's this dx thing that's happening. But for polynomials, so that's fine. But let's say I take a function in two variables, and really what's happening. Oh, sorry, xy. So you go in the multivariable case, the way you sort of, when you take the total derivative, you take the sum of the partials, but there's this dx and dy that's sort of separating, it's telling you which ones to do it. In the one variable case, that dx is not doing much. So really what's happening in this graded example here is that then you just associate dx with x. So you're just saying that dx is not actually a new thing, it's just going to be x. So that's why you don't go down a level. So really what you should be thinking of this version is the 1 over n plus 1 x n minus 1 dx. But now I said I don't want this new variable dx, I'm just going to turn this back to x. So that's what is happening. So that's that graded ring example, and that's where that's coming from. And it still works here where I turn this into x and I turn this into y. It just gets more complicated. Formula. So hopefully that answers your question.
Yeah.
Is the derivative unique? So if you're given a ring, and can there be two different derivatives?
Yes. So for every ring in every module, the 0 is a derivation. So even for polynomials, I have at least 2 derivations, the standard one and the 0 run. And in fact, for polynomials, I have infinite derivations. I just need to determine where I send x. But if I pose a condition that dx has to be 1, there's only 1 derivation. But in general, derivations are not unique. But you can probably get some uniqueness when you say, okay, well, which ones have an integration that satisfy FTC1 and FTC2? And in that case, then they could be unique in some sense. But in general, I would not say derivations are unique.
Okay, if there are no more questions, let's thank JS again.